Thanks for the introduction and thank everyone who are coming to my talk. So today I'm going to talk about the communication complexity of XOR functions. Okay, so first, what are the XOR functions? So let f be a function that maps some an input from some domain x to one bit 0, 1. Then its n-fold XOR is also a function that maps n inputs x1 up to xn also to one bit. So its n-fold XOR f to the n is a function that maps x to the n to one bit 0, 1, such that f to the n applied on x1 up to xn is just the value, the XOR of the f value applied on each of the input coordinates. So you compute f of xi on each xi and then output the XOR. So for any function f, we can define the XOR, n-fold XOR in this way, and it has n times more inputs and it also output one bit. So today's talk will be mostly focusing on the relation between the communication complexity of functions f and f to the n. Okay, so in general, what can we say about the complexity of these two functions? So first, we can always say the following in any reasonable computation model. Let's say, suppose in some model, we have an algorithm A that computes f with probability 2/3 and with cost C, where cost can be running time or communication or query. Then here is one naive algorithm for f to the n. Right. So we can simply look at the n input coordinate and then apply this algorithm A on each of the coordinates and get n output bits, which may or may not be correct. And then we just output the XOR of these n bits. Right? So you output the XOR of I from 1 to n, the algorithm A on each of the coordinates. Right? So this is one naive algorithm that we can always, one naive thing that we can always do. So what is the performance of this algorithm? So first, its cost is at most n times c, right? Or maybe n times c exactly, because we need to run a n times. And also we can verify that its success probability, the probability that this algorithm, this naive solution is correct, is actually half plus something exponentially small in n. So it's slightly better than random guessing. Okay. So this means that for any function f, if we know its complexity, then this gives an upper bound on the complexity of f to the n in some form. Now we can ask the question, if we are given the complexity of f, can we say something about the lower bound on the complexity of f to the n? And in particular, in which cases can we say that this naive algorithm is actually optimal? In other words, giving cost, assuming that the algorithm has cost much smaller than n times c, can we say that the success probability must be something like half plus something exponentially small in n? So this kind of a statement is called a strong XOR lemma, and it usually has something to do with hardness amplification. For example, here, if we have such a statement, then that means that giving some function f that is moderately hard, it's hard to compute with some constant probability. And just by XORing itself a few times, we get a function that is very, very hard. It's hard to even approximate with some exponentially small advantage. And also it has a connection to lower bound questions in streaming and sketching algorithms. And the focus of this talk will be about a strong XOR lemma for randomized communication with bounded rounds. Okay. So before I state the exact main results, maybe let me just define some notations for this communication model. It's the standard randomized communication. Just a quick recap. So we have two players, Alice and Bob. Alice receives some input X, and Bob receives some input Y. And it's randomized communication, so they both see some random bits, share random bits R. Then after seeing this, the communication starts where they send messages back and forth, and every message can depend on all the previous messages and everything the speaker is supposed to see, like the input as well as the public randomness. And this is a bounded round communication. So we have use small r rounds of communication. So and let's just denote the collection of messages or the sequence of messages by M1 up to MR. And in this model, what is the communication cost? It's just the worst case number of bits sent in this process. So we look at what is the total number of bits that are sent in all these R rounds. Okay. So now we have the communication cost of a communication protocol. Then to study the XOR function in communication setting. So what is the XOR function? We simply generate n input pairs. Let's say, okay, so we generate n input pairs and we give Alice all the X side, so X1 up to Xn, and we give Bob all the Y side, like Y1 up to Yn. And then we ask them to compute what is the XOR of the n, the function f evaluated on the n pairs. So we just ask them to output this with R rounds. Awesome. Okay. So the main result that I'm going to talk about is the following lower bound on the complexity of f to the n. So we're going to prove that the randomized, quite a bit bigger. The randomized communication complexity with R rounds of f to the n, assuming that we require the protocol to succeed with probability half plus 2 to the minus n, this must be at least n times some function that depends on R, is R to the minus R, times the complexity of f, also in R rounds, but with success probability 2/3, then -1. So on the left-hand side, we have the communication complexity, the smallest communication cost of all protocols for f to the n in R rounds that succeeds with probability half plus 2 to the minus n. And that must be at least n times the communication cost of f, also in R rounds, times something that depends on number of rounds, then -1. Right? Yeah.
It's worth saying, like if you didn't pick 2/3, or if you pick, oh, you're about to say.
Yeah, I'm about to say that thing, right? So here there are two constants that are not actually important in the statement. One is this 2 to the minus n, the other is this 2/3. So actually, this 2 to minus n, you can replace it with any constant, and 2/3 you can also replace it with any constant between half and 1. This is because, like, by just repeating your protocol a few times, you can always increase your communication cost by a constant factor, and then increase this thing to anything close to 1. So, like, for any constant that is between half and 1, this is within a constant factor of each other, and the constant will be absorbed by this other.
I more meant normally you would drive the error down to much smaller, but since you're in the bounded round case, you can't do that.
We can run instances in parallel.
No, but I mean, like if you had a protocol for computing f with error probability 1/3, you could repeat it.
Yeah, yes. He said you can run them in parallel.
You can run
the number of rounds is the same.
Yeah, number of rounds is the same. The communication increases by the number of copies because you can run them in parallel.
There's no bound on the randomness if that's what you worried. You can just do several copies of the same protocol.
Well, what I'm bothered by is the fact that if you did that, if A computed f with error probability 1 in n squared, then this wouldn't be true. Like then the XOR would be, just by the union bound,
Oh yeah, so that requires you to repeat things super constant number of times. Yes, and that's actually, that will be related to some open question that I will mention at the end. That is whether we can prove something like this, but in the other regime where, let's say, the success probability of the of n f to the n is a constant. Let's say when this is a constant, can we say that this must be something like 1 minus 1 over n? Yeah, that is something that is another, that is a different regime that we don't know how to prove
Oh, I
it.
see.
Yes.
When you say that we can replace 2 to the minus n by any constant, you mean like 2 to the minus constant times n?
Yes. Yeah. That is buried somewhere in the proof. I don't see a black box way to see that it is true, but we can actually replace this by any c to the minus n.
Okay.
Any other questions? All right. So I guess this result, this statement is most interesting when r is a constant, because in this case, this r to the r also is also a constant, and this statement just simplifies to left hand side is at least n times the cost of f then minus O of 1. Right. This basically means that as long as the complexity of f exceeds some given constant that depend on r, then we have that the best thing you can do is just to repeat independently n times. The complexity has to be omega n times more. And also this lower bound looks a bit strange because of the minus O of 1 term. And it turns out that this is actually necessary. We cannot hope to get the same inequality without the minus O of 1 because of the following simple counterexample. This is needed. Let's think about the case where f is simply the XOR of the first input bit. Okay, so this is some valid function, and then the communication cost of this function is just 2 bits. They can exchange the bits. And then what is the communication complexity of f to the n? F to the n, again, is also a bunch of the XOR of a bunch of input bits. Then the players, Alice and Bob, can first locally compute the XOR of their corresponding input bits, and then just exchange the outcome of the XOR. So again, f to the n will also have communication cost too. This means that even if we require the communication, the success probability to be 1, the complexity of f to the n still does not increase linearly in this case. So we cannot hope to remove the O of 1. Maybe let me also mention that the focus of this talk will be about this exponentially small probability 2 to the minus n. And it turns out that, as I will also mention later, if we replace this probability by constant, let's say 2/3, then the result is actually known. I will mention that later. But with exponentially small advantage, this lower bound is not known, even if r is equal to 1 for one-way communication, and if without the factor n. Right. So it was not known for one-way communication whether f to the n needs at least as much as communication as f if we only require the success probability to be something exponentially better than r.
Is the case of r equals 1 easier, which is just information basically?
From the proof, it's not. I tried to think if there's an easier proof, but I don't know. Just because like the message can arbitrarily depend on all the coordinates, all the xi's. So it may correlate the instances in arbitrary way, like even for one way. Yeah, at least I don't see a simpler proof for this case. All right. So, okay, good.
So one more question. Does it hold for any r, or is it r has to be constant?
This inequality holds for any r, but when R is too large, then this absolute minus R will absorb the complexity. Yeah. Okay. Let me also mention that we also prove a distributional version of the same theorem. Basically says that if a distribution input distribution mu is hard for F, then we show that the product of the distribution mu to the n is actually hard for the F to the n function as expected. And basically we show that if round C and cost, sorry, round R cost C protocols for F have success probability at most half plus alpha, alpha over 2 under mu, then round R cost say n times C divided by R, something a little bit smaller than n times the cost protocols for F to the n have success probability at most half plus alpha to the omega of n divided by 2 under the product distribution mu to the n. This is true as long as alpha is something small compared to n, compared to R, and also C is at least log 1 of R. Oh, sorry, log 1 of alpha.
Is this just minimax, or is there something else?
Yeah, so I would say that by applying minimax, we can, it's standard argument that we will be able to show that this theorem implies the above one. And then the actual proof will be focusing on this case where we have a fixed input distribution mu for F, and then the goal is just to prove a communication lower bound for F to the n under the product distribution. And that will be the main focus of the rest of the talk, where we just assume that we have a fixed input distribution. And then that this theorem implies that the original one is a standard argument that I will, and let me just not cover today.
I know some more person that comes on. So what happens if the left side, the rounds is there any better upper bound if the rounds on the left is allowed to be much bigger than R?
It depends. I guess there are like pointer chasing problems where there's a big difference between R and R+1 rounds. Then for those problems, I guess it will be easy if you allow even more than one round.
If the thing on the right is, yeah.
Yeah, I guess it's really, so if you want to prove something on the left side with a larger round, then you should compare to the same round complexity for F. Yes. Any other questions before I move on? All right. So it turns out that the starting point of the proof, where we will focus on this distributional version, is an XOR lemma for information complexity. An XOR lemma for information complexity. This is by Barak, Brueggemann, Chen, Rao from 2010. So without formally defining what information complexity is yet, basically what this lemma says is that the information cost, information complexity for F to the n, if we want it to be, if we want the algorithm to succeed with probability 2/3, this must be at least n times the information complexity of F minus O. So the difference here is that this is a lower bound for F to the n if we only require the protocol to succeed with some constant probability instead of exponentially small advantage. So in the next part of the talk, I will first give an alternative view of this lower bound proof that proves this information complexity XOR lemma. And then I will talk about how to generalize this error probability to exponentially small advantage. So before that, let me also mention that ultimately our lower bound proof technique has to be significantly different from this XOR lemma proof, because the strong XOR lemma with exponentially small advantage here for information complexity is actually false. There's a counterexample for it. So we have to use the fact that we're working with communication, not just information. And then, so I'll get to this point towards the end of the talk.
Rounds.
Oh yeah, this is without the number of rounds, yes. And the same thing also holds if there's a round restriction.
Sorry, the same thing also holds
if there's a round restriction R, the same inequality for information.
You might need to find information complexity.
Yeah, I'm going to do it right now. Yes. So okay, so yeah. So first, maybe a quick recap of information complexity. Okay, so as we mentioned that we are going to work with some fixed input distribution. So let's say we're going to work with input distribution mu. Okay, and let's also fix a protocol for some function. Let's say just fix a protocol pi. Then by running this protocol on this input distribution, this defines a joint distribution of everything that is involved in a communication protocol, including inputs and the transcript and also the randomness. So this defines a joint distribution. Let's also call it pi. That's usually what people do in information complexity notations over all possible, let's say, input pairs X and Y, and also public randomness R, and also the messages M. And then in information complexity, instead of bounding what is the number of bits that is sent during the whole process, we'll care about how much information is revealed about each other's inputs during this process. So for any function, so for this distribution, under this distribution, we'll define the information complexity of this protocol on this distribution to be the mutual information between Alice's inputs with the message conditioned on everything Bob knows initially, the public randomness and Bob's input, Y. Then plus the other term that is symmetric. The information revealed about Bob's inputs through the communication conditioned on everything Alice knows at the beginning. So this is how much the communication reveals about Alice's inputs, giving what Bob knows at the beginning, and the other term is the other way around. So it's okay if you haven't worked with information complexity. The rest of the talk will not focus on any detailed calculation that involves this definition, but there are just two things that you need to remember for information complexity. One is that this is not about the number of bits that is communicated through this process. It is about how much information is revealed about the other party's input through the communication. And it turns out that the information cost, this term, for any protocol is always at most the communication cost, number of bits that is sent in the process. And the other thing is that when the number of rounds is bounded, when R is a constant, for any function, the information complexity, the lowest possible information cost for any protocol for this function is basically the same as the communication cost, but up to an additive error. So this means that for any function, if you have a protocol for this function with low information costs, then you can convert it to another communication protocol with almost matching communication costs, but at the cost of increasing the error by some additive constant. So this is usually fine, but it's not actually relevant. It's not actually useful for our setting directly because we care about exponentially small advantages. So this additive thing will actually destroy that. Yeah, so, okay, so let me first say what is this XOR lemma. Yeah, so what is this XOR lemma? So what they proved is the following, and then, yeah, okay. So what they prove is the following. If there exists a protocol pi for f to the n under the product distribution mu to the n with cost, let's say information cost at most I, then there's another protocol for f under mu with cost at most I over n plus O of 1. So roughly 1 over n times the cost of pi. Yeah, I'm going to try. Yeah. So now let me present an alternative view of the proof of this statement, which is technically equivalent, but in a different language, and it will be more generalizable to our setting, as we will see later. Okay, so how do we prove this statement? Now we are giving a protocol pi for f to the n. The first step of the proof is we're going to decompose pi into two protocols, smaller protocols, pi smaller than pi n and pi smaller than n, such that pi n is a protocol for f with some information cost IA, let's say. And then pi smaller than n is another protocol, and it's for the n minus 1 fold of f with some other cost I sub b. So on one hand, this is a decomposition in the sense that the two problems that these two protocols are solving has total fold that is n. On the other hand, this is a decomposition in the sense that no matter what these two costs are, they will sum up to the cost of pi, maybe plus O of 1. So, okay, so this is the first step that we'll show later, but then I claim that once we have this will already imply the statement above. This is just because we can recursively decompose f pi smaller than m for f to the n minus 1, and we get a protocol for f and another protocol for f to the n minus 2, and then we keep doing this n minus 1 times, and eventually we will get a list of n protocols, and they are all for f, such that the total cost of these n protocols is going to be I plus O of n. Then this means the best one has the claimed property. So we just recurse pi smaller than n, and then obtain n protocols. Such that the total cost is I plus O of n. Okay. So, any questions so far? Okay. Yeah. Next, I will say this is actually a very simple decomposition, like how giving a protocol pi. What are these two smaller protocols? So let me just describe these two smaller protocols for these two functions. Let me do. So, okay, so let's first see what is the first protocol. Pi recall pi n will be a protocol for f, so it has one input pair x and y, and would like to output what is the f value on this pair. So the idea is that we are going to generate, so this is one pair. We're going to generate a big input with n input pairs, where this xy is one of the pairs, such that after generating this pair, the pairs are going to run the big protocol pi that they are given. And then from there, from the output of the big protocol pi, they're going to try to figure out what is the f value for that particular coordinate. And recall that we are working with information complexity, so running pi itself involves a lot of communication, but that's fine. We'll show that because now the input is smaller, so the information cost is actually not as large. So, okay, so let's say this is the input pair that they are going to generate. Big X and big Y. And then for pi n, they are going to view their inputs as the last coordinate of this big vector. So they're going to set xn to x and yn to y. Okay. And then they are going to use public randomness to sample the first n-1 coordinates of y. So publicly sample y smaller than n from the input distribution. So this part is publicly sampled. And then they let Alice to privately sample the first n-1 coordinates of x. Conditional y smaller than n, also from the input distribution. So this will be private. Now, so Alice and Bob have generated the whole input vector jointly with no communication. And in particular, Alice knows the entire x vector and Bob knows the entire y vector. So this allows them to run the protocol pi on this generated pair. Okay, then after running pi, they know that what is the XOR of the f value for all coordinates. Sorry. And recall that their goal is to just compute f of the last coordinate, but observe that Alice actually knows everything about first n-1 coordinates through the public or private random points. So we will just let Alice send the XOR of the first n-1 coordinates for Bob to XOR it out. So let me just write it. Right? So I claim that if pi computes the XOR of all n coordinates, then this is a protocol that computes the f value of the last coordinate. We haven't analyzed its information cost yet. Is it clear? Then the other protocol is basically symmetric. It's almost the same. So
when you say run pi, you mean that the players are going to both run it? Like Alice knows?
Yeah, Alice pretends that she only knows x, and Bob presents that he only knows y, and then they will just run protocol pi on their joint inputs, and then that has some communication. At the end, the protocol will let them learn the output. And the other protocol is basically the same. And this time we'll embed the actual input into the first n-1 coordinates. And then we let the players to publicly sample the last coordinate for x, and we let Bob to privately sample the last coordinate of y, condition of x. So publicly sample xn from the input distribution, and also Bob privately sample yn conditional xn. And then they again have the input pair, and then they will run pi on this pair. And now Bob knows everything about the last coordinate, so Bob will send the f value of the last coordinate, and this allows Alice to XOR both of them to XOR out the value of the last coordinate, so that gives the value. Okay, so let me not do the detailed analysis of the information cost of these two protocols. It's almost by definition. You can write from the definition of information cost, write down the information cost of these two protocols and do the calculation that verify that they actually sum up to the information cost of pi. And just intuitively, why this is true? This is just because they are both run. Except for the last bit, the only part that involves any communication is this last step that they run pi. And then again, because information cost is about how much information is revealed about the actual input. And in both of these two cases, the actual input is much smaller than the whole input vector x. In one case, it's only the last coordinate, and in this case, it's only the first n-1 coordinates. So we can actually show that the two things will add up to the information cost of pi, the information revealed about the entire vector. And it's a 3-line calculation, but let me just not do it here.
Perhaps
Just for the 3-line calculation that you say is straightforward, crucially analyzes both of them together, right?
Yes.
Like you cannot analyze one and then analyze the other. That is not a straightforward calculation, but analyzing them together is a straightforward calculation.
So you can analyze each one of them and then write out what is the information cost of that thing in terms of the like mutual information or whatever
you use
defined.
the properties of mutual information.
Yeah, you eventually when you use the property of mutual information to say that they add up to
And also perhaps imagine that the constant that comes out is just the fact that you have to send an extra bit on.
Yes, exactly. So the O of 1 is only because the last 2 bits that is sent in the 2 protocols.
Yeah, but then actually you need to say something about, I mean, you're doing the same thing recursively n times, right? So
Yes.
to sound said it's a constant overall.
So it's actually O of n overall, but it's fine because we divided by n, so that becomes a constant.
The fact that you switched to what was public, we're going to see that coming. It doesn't have to do with the 3-line.
Oh, you mean the part that is public versus private? That is actually important in the calculation because okay, I guess in the definition of information cost, the players only both know the public random bits that is put in the condition. So the players are not supposed to know the other player's private randomness. And if that knowing, okay, if we put something that is private into the public randomness, that can actually increase the information cost. Like maybe just
I meant in the second protocol, maybe you're answering my question, I'm not getting it. In the second protocol, you flipped it, right? Like Bob, everybody knew.
Oh, yeah. Yes. So the second part we flipped that the public thing is in X and the private thing is in Y. And this is because like eventually we will be applying chain rule of mutual information. And then if we look at X, this will be like the information revealed by X, and this will be the information revealed by X smaller than n conditional Xn. Yes. And also there's another reason that this will be helpful, as we will see later. But in the information calculation, this is also already used required. Any questions? All right. So one thing let me mention here is that it's useful to keep in mind is that so far we have three protocols, pi, pi n, pi smaller than n. It's useful to view all three protocols as the same distribution. They have the same underlying distribution, except we just view different random variables as different components of the protocol. So what I mean is that here, like in both of these two protocols, they still generate a big input vector x and y, and then the input vector together with the communication history has the same distribution as pi. So we just view everything has the same distribution, but in pi we view both big vectors x and y as the inputs and the communication as the communication. And let's say in pi n we just view the last coordinate as the input, and we view y smaller than n plus whatever is used in public randomness in pi as a public randomness, and so on. So it's useful to view all three as the same distribution, and they just different random variables are called inputs or public randomness or so on. Yeah. Now this decomposition works as long as pi outputs the correct answer. So which means that if pi has success probability 2/3, then this decomposition and iteratively decomposing it will also give a protocol f that is also correct with the same probability. Now, in order to prove the strong XOR lemma, where we assume that we have a protocol for f to the n only with exponentially small advantage, and we are still going to apply the same argument, then we need to prove something stronger. That is, if pi for f to the n has success probability half plus something exponentially small in n, let's say slightly sub-exponentially small in n, then we want to show that this is already sufficient to imply that there's a protocol for f that has success probability some constant, let's say plus and we are still going to use basically the same decomposition, and the main challenge here is that throughout this iterative process, we actually want to increase the success probability of the protocols. So this may sound a little bit strange at first, because both of these two protocols use pi as a black box. So we want to ensure that these two protocols actually succeed with higher probability than the protocol we have in.
So the version that you just showed before this improvement constant, just the 2/3 work.
Yeah.
Is it enough to prove the weaker version of your main theorem?
Yes. Yeah. So this is related to one earlier comment I had that without the exponentially small advantage for boundary rounds, the result is actually known. So this is implied by this 2/3 thing, and then by the information compression that I mentioned earlier. If you have a protocol with information cost something, then you can design another protocol with information or with communication. I almost mentioned that. Okay. Yeah. Okay. Any other questions? Okay. Now let me explain that such an increase in the success probability is actually possible using this view. So because we are going to work with a lot of properties of form half plus something, where this something is an advantage. So let me just define a notation in order to do this. So the advantage of some bit b conditional on some random variable w is defined to be 2 times the probability of B equal to 1 or 0 conditional W minus 1. So it's easy to see that this basically means that if we are giving the condition W, then B can be predicted with probability half plus the advantage over 2. And also, it's not hard to verify that if we have B1, B2 that are independent condition on W, then the advantage of B1 XOR B2, the XOR of the two bits has advantage equal to the product of the two advantages by just writing out the definition. Okay, now let's see how do we analyze the protocol, the success probability of these two protocols. So let's first imagine, let's first focus on the first one, pi smaller than n. So suppose at the end of the protocol, after we run pi, we let Alice predict the outcome, the output of the function. So first, this is without loss of generality because Alice can always send Bob a prediction. And in this case, what is the advantage of this protocol? So at the end of pi n, so what does Alice know? So Alice knows her input x n. Alice also knows the publicly sampled y smaller than n. Alice also knows the public random bits used by pi r, as well as the transcript m. And also she knows the private randomness x smaller than n. But it turns out that this private randomness is actually independent of what she wants to predict. In this case, conditional all these things. So that's essentially not useful. So so Alice knows these four things. Then what she wants to predict is just the f value of the last coordinate, right? Then the advantage in this case she has is just the advantage of this last bit conditional on these four things. Okay. Then let's also do a similar analysis for the other protocol, but from Bob's perspective. Let's say at the end of pi smaller than n, if we let Bob predict output, what is the advantage he has? So again, what does Bob know? Bob knows his input y smaller than n, and the publicly sampled xn, as well as the public random bits r, and also the transcript m. And also he knows the private random bits, but that turns out to be again independent of what he wants to predict. So, and in this case, the advantage he has is the advantage of the XOR of the first n minus 1 coordinates. That's the goal of the protocol. Again, conditional these four things. So it's an important observation here that in these two cases, if we let Alice predict in pi n and we let Bob to predict in pi smaller than n, then what they know that will affect the prediction is exactly the same set of variables, xn, y smaller than n, r, and m. Again, it's useful now to view that both of these protocols as the same distribution. Now in the same distribution, what Alice knows and Bob knows in these two cases are exactly the same. And what they want to predict is these two bits. And because this distribution is actually generated or induced by the protocol pi, these two bits are actually independent. This can be proved by just the rectangle property, by using the rectangle property of the communication protocol. So it's an observation that in the same distribution, these two bits x f applied on the last coordinate is independent of f to the n minus 1 applied on the first n minus 1 coordinates conditioned on these four things. So what does this mean is that by the second property of this advantage thing, we have that the product of these two things is equal to the product, is equal to the advantage of the XOR of these two bits, which is exactly f to the n evaluated on the entire vector. So this is equal to the advantage of f to the n applied on the entire vector given the same thing. So this is an equality that has a good form, has a good direction. Basically, it says that this basically relates the advantage of these two smaller protocols to the advantage of the big protocol of pi. And it has the form that the product of these two things is equal to the last thing, meaning that if we know that this is something sub-exponential in n, slightly sub-exponential in n, then we get to know that either this is very, very small, either this is very large, that is very close to 1, or this will be sub-exponential in n minus 1. And then if we keep doing this n times, then we basically get n protocols, and the best one of them will have the good advantage. How many minutes do I have?
We should end by 12:30, if not.
Oh, okay, that's a lot of time. So maybe I will 10 minutes.
Yeah, sure.
Okay, 10 minutes.
Could you perhaps repeat why do you get the conditional independence, the first line of the observation?
Say it again.
Can you repeat why do you get this conditional independence?
Oh, this conditional independence. Yeah, this is because the rectangle property of communication protocol. So you assume that the whole disjoint distribution is induced by this protocol pi, right? So you imagine that at the beginning of the communication, because the inputs are sampled from product distributions, so these two are independent, even conditioned on these three without the communication. Then every time one player sends one message, you can show that conditioned on these three things, the message is only a function of, only depends on one of these two terms and is independent of the other. So you can literally prove that, induction, prove that this.
The whole trick is getting pi, the simulating pi to be,
Yeah.
fast.
All right. So I guess in the last 10 minutes, let me briefly explain what the technical challenge in using this equality, and what is the solution to that thing. So first note that this equality is actually a pointwise equality, meaning that for any given value of this quadruple, we have that the advantage, the product of these two advantages is equal to the advantage of the last thing. But when we talk about the advantage of a protocol in general, what we actually want to say is the expectation over the condition, the expected value of this quantity. So ideally, what we want is that the same equality, or maybe inequality with the same direction, but about the expectation of these three terms, right? So because the expectation will actually equal to the exact advantage of the protocol. So if we had this expectation, the product of two expectations is equal to the expectation of the right-hand side, then this is a good protocol that we can, this is a good inequality that we can actually use. But it turns out that this is not true. So let me briefly say how we actually use this equality. So is it clear why we need expectation here? The point why is it not what we want.
It's not clear why it's not true, but
Okay. Yeah, I guess it's not clear why it's not true. Yeah, but, so just for simplistic notation, let me call this term A, and this term B, and the right-hand side C. So what we have is that A times B is equal to C for three variables, but we cannot say anything about states. We don't know how to say anything about the expectation. And suppose C is related to the advantage of pi, and that's some very small number. Let's say the expectation of C, which is the advantage of pi, which is related to the advantage of pi, is some very small number epsilon. So in order to use this equality, we let's examine two extreme cases for this distribution. So this random variable has expectation epsilon. Then there are two extreme cases for this to happen. The first case, maybe this random variable is actually taking epsilon almost all the time. So this is one case that C is about epsilon. Let's say C is equal to epsilon with probability almost 1. So it turns out that this is actually the good case where we have the equality for expectation in the right direction. So this is because we have that the expectation of A times the expectation of B by Cauchy-Schwarz. This is at least the expectation of square root of AB squared. Right? And then because if C has a distribution, if C takes the value epsilon almost all the time, then this is basically square root of epsilon, and this is basically epsilon. And then this means that the advantage of these two smaller protocols, the expected value, the product of the expected value is actually at least epsilon. Then we know that at least one of them has good. So either the one for F has good advantage already, or the other one must increase by some multiplicative factor. So this is the easy case. And the other extreme case may be C is taking value epsilon, C is taking has expectation epsilon, because with epsilon probability is taking value 1, and with other probability is taking value 0, because C here is something between 0 and 1. So let's say C is equal to 1 with probability epsilon and 0 otherwise. So turns out that this case is very similar to the direct product theorem case, where so here the XOR lemma, we have n inputs and asked the protocol output what is the XOR of the n input bits. And in the direct product case, we ask the protocol to output the value of every single coordinate and ask what is the probability that this can happen. And there were results on that showing that the probability has to be something exponential small. And then if we think about what this means is that with epsilon probability, we know the value of the XOR exactly, and otherwise we know nothing. So this is actually very similar to the direct product case where like with some small probability, we know everything. And it turns out that the idea from the direct product theorem proofs can be some variance can be used here. So the idea is that let's denote this event by U, and then we're going to study the distribution that is pi conditional U. Okay. So pi is some well-defined distribution, and then U is an event. We can study pi conditional U. But pi conditional U is not necessarily a protocol, right? So this is one first issue. But the idea is that we will actually monitor through this iterative process how close to a protocol this arbitrary distribution is. So, so first we'll monitor the closeness. We'll also monitor the closeness to actual protocols. Throughout the argument. And eventually we may get some distribution that is very close to an actual protocol for function f, and then we can show that that can actually be turned into an actual protocol without increasing the error or cost by too much. Okay, so this is one thing. And the other issue with conditional on U is that if we remember the information cost that I mentioned earlier, that I defined earlier, it is actually a sum of mutual informations. And mutual information is actually an expectation, right? So if we look at two random variables, x and y, in general, the mutual information, one way to say the mutual information is that what is the expected value of log of the probability of x and y divided by the probability of x times the probability of y. So because this is an expectation, then conditional on, if we try to condition on some small probability event, this may actually increase the cost by a lot, right? So it can increase, if this has probability p, then it may increase this expectation at least by 1/p, for example. But this is not acceptable because we don't want to lose some multiplicative factor each time. And the solution here is that instead of, okay, I guess the reason here is that the quantity inside the expectation it's not guaranteed that it has any concentration. We just know that the expectation is equal to something. And then this means that conditional on some small probability event, the value can be very different from its original expectation. And the solution here is that instead of looking at this expectation, we will work with its exponential version. So we'll work with the expectation of the probability of x and y times the probability of x times the probability of y throughout the entire argument. So overall, the argument will not be about information complexity, which is defined this way, but we'll define all the costs of all the protocols and the intermediate ones via this definition, where we just look at the expectation of this probability divided by two probabilities. So intuitively, whenever we want to prove that this is bounded by some number I, we will instead show that this exponential version is at most 2 to the O of I. Right? So this will not only imply that the expectation is I, but also says there's a strong concentration. It cannot be too large if we condition on some small probability event. And in particular, if we condition on some event with probability P, it can only increase this number by at most a factor of 1/p, and effectively this only increases this I that corresponds to the communication or information by an additive O of 1/log p, log 1/p. And this is more affordable as like every time, in every iteration, we only lose an additive communication.
So I have a lot of questions, but I'll try to ask just a few little ones. So
Yeah.
I don't know what you mean by monitor closeness to the protocol, and also, so I don't understand why why it helps to get rid of the log, and maybe it would be helpful to say somewhere. Maybe it'll help me to understand that where the bounded rounds comes in.
Yeah. Okay. So I guess first thing.
On the slide, everything's good.
So first the idea is that we are going to look at this distribution pi conditional U. So pi is something induced by a protocol, but pi conditional U is not necessarily a protocol because U can be some very arbitrary event. Then what we are going to do is to measure how close to a protocol this distribution is, and more formally, let me just say it here. The notion that was used in previous work is to measure. Let me actually write it here. Measure the let's say Alice sent all the messages. So look at the mutual information between each Alice message with Bob's input, conditional on what Alice knows, and also the previous messages. Then plus the other term, that is what is the mutual information between Bob's messages with Alice's input, conditional on what Bob knows and previous messages. So for an actual protocol, this sum should be 0, right? So they should be independent. And then what happens here is that we are going to monitor throughout this iteration like decomposition, what this value is. We can first show that a decomposition actually decomposes this value as well to for this pi and pi smaller than n. And also we can show that if for an actual protocol, if we condition on some small probability event, then this value will not be larger than log 1 over the probability of this event. So initially, if this probability is not too small, then this closeness to this is not too far from the actual protocol in this sense. And actually, and finally, if this is close enough to an actual protocol, then you can actually convert it to an actual protocol without increasing the cost by too much. This makes sense. So.
Kind of.
Okay. Yeah, so I guess one thing I should mention here is that throughout the argument, we will not only work with protocols, but we will work with such distributions that are not necessary protocols. And also, instead of just looking at their information this cost and also the error, we will also monitor. We will also keep track of this closeness to the actual protocol and make sure that the final protocol we get is the final thing we get is actually close to an actual protocol, also with small cost. And also here, yeah, I guess so. Why do we need to remove this log to work with this notion instead of the mutual information? This is because suppose pi is some protocol, and if we condition on some small probability event, then what this means is that when we measure the information cost of some two random variables, if we add a condition here, then it's basically adding, at least it's adding something here. This will also affect the probabilities. So in principle, this expectation or the mutual information can increase a lot if we condition on a small probability event. Just because the quantity inside the expectation, we don't have any concentration guarantees about it. And then the advantage of using this notation is that this is the thing inside it is exponential in what we want to measure. So if we, instead of saying that this is at most I, we try to prove that every time we try to say this is at most I, instead we try to say that this is at most choose the I. Then this will not only imply that by Jensen's inequality that this is at most log of that, but also we'll say that the quantity inside here has a very good concentration. You cannot take like even 2 times this value too often. And that is the intuition.
So is the only place you're using bounded round is the fact that you're always using information instead of communication, and that only holds in the bounded round?
Yeah, bounded round, that part, actually, I didn't get to mention exactly why, but ultimately it is because of this formulation here. It has R terms, which depends on number of rounds. And because of the second issue here, we also need to turn these R mutual informations into this exponential version, which basically becomes exponential. It's expectation of like a product of R things. And there's some technical issue in about analyzing if we condition on some event, how large can this increase? And there we will lose something for each of the term there, and that's something that depends on R.
Is anything known about the case of morals?
So if, besides the information one where you have constant success probability, it's not, at least we don't. So there was no previous work, and also the current technique, I don't think it implies that.
If you did get it to work for the other, when it's not bounded around, would that give you a stronger compression result? Like, sorry, not compression, would it give you a stronger separation between information and communication?
Oh, I mean, if we prove the same thing, but for unbounded, yes, it will. So, okay, so what Tony meant was, suppose we prove the same results without the bounded rounds, then this will actually imply a stronger compression for information. Basically means that if you have a communication protocol with low information, you can convert, that will imply that you can always convert it to a communication protocol with the same communication cost as the previous information cost. So the best thing we can hope to get without without breaking that barrier is that to show that, okay, I guess I already erased that, but basically show that the communication cost of something like this must be at least n times the information cost of f. Let's say we choose this maybe -1, something like this. But if we prove something like this, it will not violate it will not break that barrier, but also is not impossible. All right. Yeah, I guess I will stop here.
Anybody else have questions?
Perhaps can you say it? Is it too technical to prove that when you have this condition, then you can prove that inequality on the right hand side, right? So if it's an actual protocol, you get 0. But can you say more words of how this would go about?
Yeah.
Or is it too technical?
I remember it's not a hard calculation, but it's like maybe 10 lines. It's almost just by definition, and then you use the fact that like you write the mutual information as expected KL divergence, and then use the fact that KL divergence has the property that if you condition something, it's not going to increase by too much. It's not complicated, but it's just 1 lines.
And perhaps another question, which is more open-ended. Do you expect that anything like this would hold for multiple parties?
That's a good question. So, yeah, I don't think there's a good notion for information complexity with multi-party communication.
You mean number in hand?
Any model, just more than 2 parties.
Yeah, I don't know any good notion for information complexity with more than 2 players.
But number in hand, we have it, right? Isn't it the same?
It is.
Yeah,
Don't you just look, instead of 2, doesn't it just like?
Yeah, you'd have to decide what
I think you're
mutual
thinking number on
information.
forehead, I'm guessing.
Okay. Oh, yeah. I guess for number in hand, that's right. So
I think you just sum up all the players and how much.
yes.
You need to figure out which mutual information makes sense, right?
Right. I guess you can say something like for each message, for each, let's say that it's a broadcast, and then for each message, what is the mutual information between the speaker's input conditional, like for each receiver, what is the information revealed? But I don't know if this will exactly apply to this regime. Seems different, but it's not impossible.
It's just open-ended.
Yeah, it's a good direction.
Excellent, thanks. Again.